All right, we're going to go through some speeds and feeds here. I'm going to show you how to do this for the milling machine. This can be a little bit of review. You've already done this for the lathe, and everything is very similar here. We just have to add on to it a little bit. So let's say we're thrown in a scenario, and we have, I don't know, we'll say it's a 3/8 end mill. It has 2 flutes, and we're cutting aluminum. And we want to calculate out our speed and feed. So to do that, we're going to do the same formula we've done before. So it's going to be the cutting speed times 4. We can go to this chart, and this chart is the same one you've seen previously, except for we just added a chip load column to it. Otherwise, the speeds and feeds, being that it's a high-speed steel, go away. So it's a high-speed steel cutter. It says it on the top underneath that little blip that just popped up. Anyways, and this is the document for a high-speed steel cutter for milling. So surface speeds, these are all going to be the exact same numbers as they were for turning. Nothing's going to change because you're using the same cutter material type, the cutter material, and it's the same material, the same list basically. So if we go through here, all right, we can identify that, all right, the material is aluminum, so we know we're going to use aluminum and its alloys. And that's 200 to 500 surface footage. So what we would do then is we'll always do the low range of that. So we're going to follow the formula, cutting speed times 4 divided by cutter diameter. So to figure out the RPM, I'm just going to pencil it in here. RPM is going to be equal to 200 times 4, and that's going to equal 800 RPM. 800 to start with, but then we're going to take 800 and we're going to divide that by the diameter of our cutter. So we take 800 divided by 3/8, which is 0.375, and that's 0.375, and it's going to equal 2133 RPM. So this is the true RPM that it comes out at. So RPM is 2133. So that's how you do the calculations there. You're just going to take your 200 times 4, and then that's going to equal 800. Take 800 divided by 3/8, and you're going to get 2133. So same formula as we learned in turning. The only thing that's different now is on milling, your cutter is actually what spins. On the lathe, remember, the work actually spun. On the milling machine, the work is fixed, and the cutter will spin. So that's how you would figure out the RPM. And then to figure out the next step is if you actually want to feed it with a power feed. Some milling machines have a power feed option. You're going to take it to the next step and figure out the calculation. Mills will always feed in IPM, or inches per minute, versus the lathe. Remember, the lathe fed in inches per revolution. Well, this is inches per minute. So it's slightly different. The calculation is going to be different here. So to do this, you need to take the RPM. So we're going to take this 2133, and I'm going to drop down here, and this is just going to be the IPM. Oops. And we're going to take the RPM of 2133 times the number of flutes. All right, the number of flutes we were told here is 2, so we take it times 2, and then times the chip load. Well, the chip load is what we see over here on this document, the chip load per tooth. So on this, we can see it gives us a range of 3 to 6 thousandths. So we're going to work as we do on the low side of things, and then as eventually we work our way up, but we're going to start at 3 thousandths. So we take 2133 times 2 times 0.003, and that is going to equal, let's calculate it out, 2133 times 2 times 0.003, did something wrong, times, there we go. So it comes out to 12.798. And if you want to round that, I mean, you could round it to 13, you can round it to 12.8. It doesn't usually have to be that perfect. So, but that's what the math comes out at, and that is 12.798 IPM, or inches per minute. So what that means, in 1 minute's time, it's going to travel 12.798 inches if it fed at that increment. So just kind of think of that, okay, over a time frame of a minute, it's going to travel a little over 1 foot, or a little over 12 inches. And that's what that really truly means. So there's one example. We're going to do a couple like that just so you get the idea of this. So the next one here, I don't know, we're going to say this one here is a bigger cutter. We'll say it's a 2-inch cutter. Not too often will you run a 2-inch cutter, but I just want to show you kind of how it'll change things around. So I'm going to take a 2-inch cutter, and we'll say we'll just do a 2-inch face cutter. Face cutter. Okay, and we're going to have 6 flutes on it, we're going to say. That's basically 6 cutting edges. And we're going to be cutting tool steel. All right, so with that, we're going to go over to our chart, and we're going to figure out tool steel runs at 40 surface feet per minute, or it's a cutting speed of 40. So then what we're going to do is take that cutting speed of 40 times our constant, which is always 4. So cutting speed times 4, and that 4 never changes. And 40 by 4, we're at 160. And then we're going to take that 160 and we are going to divide that by the cutter diameter. Well, the cutter diameter is 2 inches, so 160 divided by 2. And we're going to come out at equals 80 RPM. So we've got 80 RPM for the cutter. Not very fast, but again, that's a good size cutter, 2 inches. And you're cutting tool steel, which isn't super high on the surface footage range. So when you're dealing with a difficult material and a larger cutter, it's going to slow your RPMs down dramatically. So 80 RPM is what you're looking for there. And then if you want to calculate it out to figure out the feed that you would run that machine at, you would go down here and try to leave that bit. So we're going to take 80 times, so 80 RPM times the number of flutes. In this scenario, it is 6 flutes times the chip load. So if I go back to the chart over here on tool steel, it says a chip load of 2 to 3 thousandths. So we'll err on the side of caution with 2. And if we calculate that all out, 80 times 6 times 0.002, we tally out at 0.96 IPM, or 0.96 inches per minute. So what that's telling us is that 1 minute's time frame, it's going to travel less than 1 inch. That's very slow. But if you imagine you're only running the cutter at 80 RPM, they're all relative to one another. So that's how you do the math on this. That's how you can figure this out, and that's how you can calculate your RPMs and your feed rate for the milling machine. Now, only some of the milling machines that we have can you actually program a feed rate in, so it's not relative to a lot of milling machines because they actually are just controlled by hand. But you could also, get a visual of, okay, and how much time you're moving. If you know it needs to move, say 12 inches a minute, you can kind of look and say, okay, well, you can kind of visualize where it's at. Even beyond that, on the milling machine, you're going to get a lot of feel, and you're going to be able to tell if you're pushing something too hard or you're going too light. Usually too hard, you'll feel the cutter kind of binding up, and all of a sudden, if you go too hard for too long, you're going to break something, usually your cutter. And if you go too light, you might hear a lot of squealing or vibration or chatter. And that, if you're nice and rigid on your tool and it's still squeaking and chattering like that, it's probably because you're feeding it too slow. So those are 2 good indicators. Otherwise, that's a breakdown of how to figure out and calculate all these RPMs. So thanks for watching.